Welcome to the Crazy Hat Chemist, so another video on gases. Bam! So today we're talking about a gas production and a percent yield problem here. Okay, all encompassing many different things. All right, so I'm going to read the question to you. It's 0.23 grams of potassium chlorate. I want you to think about that formula, try to write it down yourself before we go to the next slide. So 0.23 grams of potassium chlorate was heated using a Bunsen burner, and the gaseous product was collected over water. Question: the gaseous product was collected over water. That's a good one there for you. So it's over water again. And I want you to think about also, as you heat up potassium chlorate, what type of reaction that is, and then what the product of the gaseous product would be. And of course, there is another product as well. The temperature of the room was 26.5 degrees Celsius. The pressure of the room was 779.2 millimeters of mercury. And the volume of the gas collected was 40.9 milliliters. The vapor pressure at 26.5 degrees Celsius is 25.963 millimeters of mercury, and that's coming from a table. So what are we going to do? We're going to do the following. Number one, we're going to write a balanced equation for this reaction. Okay. Number two, we're going to calculate the number of moles of gas produced. Number three, we're going to calculate the theoretical number of moles of gas produced. And then number four, we're going to calculate the percent yield. So, all encompassing in this problem. I'm going to show you a laboratory setup of what this looks like as well. So here's what we got. This is the balanced equation. This is a decomposition reaction. On the reactant side is solid potassium chlorate. There's 2 moles of that. Okay, you need heat, and that's in the form of that Bunsen burner. You get 3 moles of oxygen gas, that's molecular oxygen, and then 2 moles of potassium chloride. Okay, that's in its solid state. So you should see this setup right here. I got that Bunsen burner moving. That potassium chlorate is inside my Erlenmeyer flask there. There's the Bunsen burner. Okay, this is a pneumatic trough, and there's water in this trough as well as in that container, that jar that's there. Okay, there's tubing that's connecting the Erlenmeyer flask all the way, and it goes underneath, inside of this pneumatic trough, inside the metal rivet parts of this pneumatic trough, and into a hole. Okay, so that any of the gas that is produced in the Erlenmeyer flask is now transferred into that jar that's tipped upside down, that is completely filled with water right now. So it's a water displacement gas collection experiment. Okay, so this is what happens here. This is the oxygen gas. You can see it bubbling there from that tube that's sticking at the bottom of that jar that's turned upside down. And at the top, there's the oxygen gas, and that's being collected over water. That's Dalton's law also. All right, so let's get moving with the math on this problem and answer all the questions. Make sure you remember that balanced equation that's right there, that decomposition reaction. Very common reaction to do in the laboratory. All right, so I got that balanced equation there at the top, and let's do the math. Okay, we're going to solve PV equals nRT, and we haven't talked about this yet at all, but this is the ideal gas law. I'm going to talk more about this a little bit later. Okay, what I'm doing is I'm rearranging the ideal gas law to solve for the moles of oxygen, because this is one of the questions that was in this, is solving for the moles of oxygen gas. So I rearranged it to solve for N, which is moles, and then I have that NO2 solving for moles of oxygen gas. P is for pressure, V is for volume, R is the gas constant, T is the temperature. So I'm going to plug in the values of which I know. I have the volume, which was given, that is the collected volume of the gas. I got the gas constant, that is a constant, and I have the temperature, and I converted that from degrees Celsius into Kelvin. I'm assuming you can do that by now. Now the thing that I'm missing here is the pressure. That is because this gas was collected over water. So I'm going to have to use Dalton's law first to get the pressure of just the oxygen gas. So I got the total pressure of the system, that is the measured pressure of the room, or the atmospheric pressure if you will, and I got the partial pressure of water. That's coming from a tabled value. Those numbers are right there. They're all in millimeters of mercury. I'm going to solve for the pressure of the oxygen gas. That's that number right there, and then that is going to be going into the ideal gas equation right there like that. Hopefully that works out well for you. You should see that the units of atmospheres cancels out, liters cancels out, kelvins cancels out, and then you have moles in the denominator of a fraction. So that means that when you solve this, you're going to get units of moles, and that's going to be right here. So that's 1.65 times 10 to the negative 3 moles of oxygen. What is this? This is the actual amount from the gas that is collected. Therefore, this is the experimental portion of this, and that's why it's the actual amount. Now I need to solve for the theoretical amount of moles of oxygen that you could have collected under the most ideal circumstances. So I'm going to start off with the amount of potassium chlorate that I have started with, and that's 0.23 grams of potassium chlorate. I'm going to cancel out the grams using the molar mass of potassium chlorate. That's equal to 1 mole. Then I'm going to use the mole ratio between potassium chlorate and oxygen to now solve for the moles of oxygen. So this value, 2.8 times 10 to the negative 3 moles of oxygen, is the theoretical amount that you could have collected if under the most ideal circumstances. Now, in order to solve for the percent yield, you need to know the percent yield mathematics and the calculation therein. And that is right here. So it's always the actual amount, that is the experimental amount. What you measure amount is in the numerator, the actual amount. And then the theoretical amount. The theoretical amount is always calculated. That is, under the most ideal circumstances, what can you obtain at the most. And then we're going to multiply this by 100, of course, because we are looking for a percentage. So I'm going to plug in the actual and the theoretical in their respective numerator and denominator, multiply by 100, and those are those numbers there. You should see that the moles of O2 are going to cancel out, and I'm just going to be left with a percentage. So on this lab example, we have a 59% yield of my product. So I could have collected more under more ideal circumstances, but I only was able to collect 59% of that oxygen from what I would have expected to collect. All right. Hopefully that worked out well for you. This is a Dalton's law and an ideal gas law problem. It's an experimental laboratory problem as well. Okay, super complicated problem, but yet if you do each step individually and solve each step individually, then it's really not that bad as long as you break it down. Okay, I am the Crazy Hat Chemist, and that's just another video, and I'm feeling kind of goofy today. Give me a thumbs up if you like that video. Subscribe to my YouTube channel. Tell your grandmother to subscribe to my YouTube channel. Tell your parents to subscribe to my YouTube channel. And I'll see you next time for more cool chemistry problems. Bye now.